Hello, in this video I'm going to solve question 7, problems set 2, lecture 3, lectures in elementary number theory. Determine all natural numbers x and y such that 3xy minus y minus 5x equals 13. Pause the video at this point and give it a try. Okay, so now let us solve the problem. We are looking for all natural numbers x and y for which the left-hand side equals to right-hand side 13. Okay, so what we can do, I want to use the theorems that I presented in lecture number 3 as much as I can, the theorems that I present in these series of lectures. Okay, of course, it doesn't mean that this is what I present here as the solution is the only way to solve this problem. Of course, you can find your own method for solving this, but I am just following my own lectures so that I want you to use the theorems that I present in the lecture so that you can be better in using them. Okay, so one way to solve this problem, for example, I can factor y between these two, so it becomes y times 3x minus 1, and I move 5x to the other side, because somehow I want to connect it with divisibility, yes? So if y is supposed to be a natural number, y times this expression is equal to this number, okay? So this means that this number divides this number. So this means that, so from here I can conclude this, and then from here, based on the definition of divisibility and assuming that y and x are natural numbers, this means that 3x minus 1 should divide 5x plus 13, okay? And you have enough experience by these problems if you have watched the previous videos on this playlist. So if I want to know my x, it is always beneficial to make this a constant. For making this a constant, I want to use this theorem, which was presented in lecture number 3. So if I know a divides b, and if I know that m is an integer, I can conclude that a divides b plus ma as well. So in other words, if I have a divisibility relation, which I know is true, if I want to, I can add any integer multiple of the left-hand side to the right-hand side. The new divisibility relation is also true, and we also learned in lecture number 3 that this theorem is also reversible. Okay, so in order to get rid of this 5, because you see this is 3, this is 5. So there is no way for me to get rid of this x by multiplying this by any integer, because when I multiply this by any integer, I will never go back to 5. So what I will do, I will multiply the right-hand side by 3, because we also had a different theorem in lecture number 2. If I know that a divides b, if I want to, I can multiply only the right-hand side by an integer m, and if this is true, this one is also true. Okay, so the next step that I want to do is to copy and paste the left-hand side and multiply the right-hand side by 3. So then this becomes 15x plus 39, okay? So from here to here, I am using the second theorem there. But now I can use this theorem again by giving the role of m to negative 5. Yes, so from here, I can conclude that 3x minus 1 divides the right-hand side minus 5 times this. Yes? Okay, but now you can see what happens if I multiply this minus 5 in, this will be minus 15x plus 5, so that is good, because that minus 15x will cancel this one, and I am left with 39 and 5, which is 44. So this means that this will give me 3x minus 1 divides 44, and that is good, because now I have a constant number on the right side, and I know it is divisible by this natural number. If x is a natural number, it means that the lowest value is 1, so this is really positive. So it's a natural number. So I am looking for all natural numbers for which 44 is divisible by. So that is an easy task, but be careful here about the direction of these arrows. So is this arrow reversible? Yes, because if this is true, 44 can be written in this a little bit weird way, but anyway, it is true. So from here, I can conclude this one. From here, I can also conclude this one, because this theorem is also reversible. So I can drop this multiple of the left-hand side. So this one is also reversible. Yes, so I can go here. But what about this one? This one is not reversible. Because when I came from here to here by multiplying the right-hand side by 3, there is no theorem that allows me to divide the right-hand side by 3. So this arrow is not reversible. Okay, so what does it mean? It means the last statement is not completely equivalent to the first statement. Okay, the solutions of this are among the solutions to this, but there might be some false solutions for this one if I choose all of them. So I have to be careful. So I have to do some trial and error. But this is a good method because potentially I had infinitely many choices to do trial and error, which was not possible. But by this analysis, I narrowed down the list to a bunch of numbers, to a bunch of finitely many numbers, so that I can do the test. So remember, I am looking for natural numbers, so I have to ask myself, what are the possibilities for 3x minus 1? So 3x minus 1, in principle, is plus or minus 1, but minus 1 is not acceptable because the problem is asking for natural numbers. So the factors of 44 are 1, 2, 4, and the next one 11, and then 22, and then 44. So let us double check. So 44 is 4 times 11. So yes, 1, 2, and 4, and 11, and 2 times 11, and 44. So these are the only possibilities. From here, 3x minus 1 equals to 1 gives me x equals to 2 over 3, which is not acceptable. 3x minus 1 is equal to 2 gives me x equals to 1. For the time being, it is acceptable. It is acceptable for this one, but it is not guaranteed to be acceptable for my original problem. Be careful about that. And 3x minus 1 equals to 4 gives me x 5 over 3, which is not acceptable. For this one gives me x equals to 4. This one will not be acceptable, and the other one gives me x equals to 50. These are the solutions for this divisibility relation. Okay, but let us see which one of them will give rise to an acceptable y as well. Okay, so this means that if you are looking for natural x's, your natural x's should be among these numbers. It is not guaranteed all of them are acceptable. So one way is to go backward, for example, here to see which one of those x's is also acceptable for this one, because you see that this one and that one are not equivalent. Okay, and by the way, this is also not reversible because there is no guarantee that that quotient is just exactly this y. So that is also not reversible. But anyway, so you can, for example, see if 1 fits here. If I choose 1 here, this becomes 2, then it becomes 18. So that is acceptable for this one. But still, there is no guarantee that it is acceptable for y. So let us just do that. Of course, I will definitely get y because I am looking for y as well. So what I do, I will put it here, and then I will find y. So if it works, instead of x, I put 1, so it becomes 2. And it becomes 18, so y becomes 9. So that is correct. So I would say one pair of numbers is this pair. If x is 4, I put it here, it becomes 11y, yes, equals to 20 and then 33. Yes, so y becomes 3. So this means another pair is x equals to 4, y equals to 3. That is also acceptable. And then what about 15? If I put 15 here, it becomes 44y equals to, if I put 15 here, if I put 15 here, 75, and then 88. Yes, that is also acceptable, so y becomes 2. So another pair is that x equals to 15, y equals to 2. So I have 3 pairs of solutions. Here, in this case, all the solutions were indeed acceptable, but I want you to understand this is just somehow a coincidence that we do not have any false solutions among these solutions because they are not equivalent. So checking them is indeed necessary. Okay, so I hope that this video was useful for you. Until the next video, be safe and goodbye. Thank you.